And hopefully the internet seems to be good today, not like some other days, which I have found was a little bit destructive, but we shall go through it. And the whole time we have is fairly large, so nothing to rush. Take your time, absorb the subjects, and let's go smoothly. So, I mean, I shall start recording a little bit later, but I think, shall we start? 52 is the number I can see. Is that a right time to start? Did you have a lecture right before, or?
Yes, sir.
Yes, sir, we have a class.
Okay. Yeah, I think that's probably is the reason that you joined a little bit later. I was a bit concerned whether you have been informed or my system was working or not, but hopefully things will be smooth. Okay, I think what I will do, I'll share the screen and just start some few things. I think we have got a you have got a system of class representative you call CR.
Sir, I am roll number 26, Ragib Hasan, sir.
Okay, just a second. Let me just point out these. And so roll number 26 in section A.
Yes, sir.
Okay, let me see. Roll number 26, section A. I can't find you. What's your name? Are you in section A or section B? I think perhaps in section B.
Sir, do section একসাথে class করছে sir. Ragib Hasan.
I know, but my timetable is the attendance register is in 2 copies. So roll number 26.
I raise my hand, sir.
So তুমি হচ্ছে রাগিব রিনাত.
Yes, sir.
হ্যাঁ, ঠিক আছে. So তুমি class representative, okay? So I will create a Google Classroom later, and I plan to upload most of this stuff from the Google Classroom when the class is finished towards the end. And also I will communicate with you so that you can pass the information to your friends and colleagues. What is important is I like communicating with you through email, okay? So I shall reveal my email in a minute. And then once you see the email, you can, all of you, I would suggest take a note of the email, and especially Ragib, you take an email and send me an email saying that you are Ragib in the ME-307. And that's when the communication will begin. Is that clear?
Yes, sir.
Okay. So once you see my email, just drop me a line saying that, sir, I'm Ragib, I'm the class representative for this, and then I shall communicate with you whenever is needed. I prefer emails because that's how I'm used to it. Okay, all right, so I think we can make a start, and the first thing I will do, obviously it's more than 10 minutes, so there is nearly 15 minutes, so there is no reason to wait anymore. I'll do the roll call first because that's a requirement. And then please be prompt in responding. So I'll start with section A, roll number 24, Apel Mahmood. Apel Mahmood. Roll number 58, Mahmoudul Hasan.
Yes, sir.
Roll number 101, Fahad Enayed.
Present, sir.
Roll number 102, Faisal Shohag. Roll number 102, Faisal Imran Shohag.
Present, sir.
Roll number 103, Salim Al Razi.
Present, sir.
Roll number 104, Sheikh Abdullah Al Kamal.
Present, sir.
105, Tasbeen Al Shifat.
Present, sir.
106, Muhammad Tanveer Ahmed Hridoy.
Present, sir.
Roll number 1, Captain Russell Ahmed Puya.
Present, sir.
Roll number 2, Abdullah Zubair.
Present, sir.
Roll number 5, Muhammad Alamgir Hussain Shoikot.
Present, sir.
Roll number 6, Shishir Khan.
Present, sir.
Roll number 8, Yasin Abrar.
Present, sir.
Roll number 10, Farhan Sadiq. Roll number 12, Mahima Ahmed Mim.
Present, sir.
Roll number 15, Abdul Hasib Hasan Zayed.
Present, sir.
Roll number 20, Muhammad Shafayat Islam.
Yes, sir.
Roll number 21, Sheikh Salman Rahim Rifat.
Present, sir.
Roll number 22, Niaz Muhammad Zahin. Niaz Muhammad Zahin. Roll number 23, Mustafa Zawad Itmam.
Yes, sir.
Roll number 24, Mashur Sihan Nirjan.
Present, sir.
Ragib, I have noted you present.
Yes, sir.
Roll number 27, Muhammad Rahat Rahman.
Present, sir.
28, Salihin Mustaqim.
Yes, sir.
Roll number 29, Fardin Ibn Ashraf.
Yes, sir.
Roll number 31, K.M. Zamiul Haq.
Yes, sir.
32, Niaz Mahmood Anim.
Yes, sir.
Roll number 33, Aisha Siddiqa.
Yes, sir.
35, Sadia Islam Lami.
Yes, sir.
Roll number 44, Shohag Yaman.
Yes, sir.
45, Abdullah Al Farouk.
Yes, sir.
46, Erin Jahan FT.
Yes, sir.
Roll number 51, Shikta Ahmed.
Yes, sir.
Roll number 52, Tanvir Ahmed.
Yes, sir.
Roll number 55, Rokia Begum.
Yes, sir.
Roll number 57, Shabbir Ahmed Faisal.
Yes, sir.
Roll number 44, Oliullah Samir.
Present, sir.
Roll number
Present, sir.
48, okay. Roll number 48, Shahidul Islam Masoom.
Present, sir.
Okay, that brings me to the end of section A. Now going to section B. Roll number 33, Naimul Hasan. Naimul Hasan. Roll number 18, Shanto Shaha. Can you hear me? Roll number 18, Shanto Shaha. Roll number 48, Mahdi Hassan.
Yes, sir.
Roll number 56, Rahel Ikram Rocky.
Present, sir.
Roll number 3, K.M. Mahmudul Hassan.
Present, sir.
Roll number 4, Muhammad Mahbubur Rahman.
Yes, sir.
Roll number 7, Shoaib Ahmed Opu.
Present, sir.
Roll number 9, Imrul Kais. Imrul Kais.
Present, sir. Present, sir.
Sabiha Noreen Haq. Roll number 11.
Present, sir.
Roll number 13, Onika Tabassum.
Present, sir.
Roll number 14, Nabila Kamal Nova.
Yes, sir.
Roll number 17, Saiful
Present,
Islam
sir.
Shagor. Shagor.
Present, sir. Yes, sir.
Okay. Roll number 19, Muhammad Abul Kalam Azad.
Sir, roll number 18, sir. 18 present, sir.
18, okay. আর
জি,
আমি
স্যার।
আছি এখন রোল নাম্বার 19, আবুল কালাম আজাদ। তুমি আছো? আবুল কালাম আজাদ।
Yes, sir.
Okay. Absent. Mustafa Rafid, roll
Yes,
number
sir.
25.
Yes,
Roll
sir.
number 30, Sakib Ahmed.
Yes, sir.
Roll number
present, sir.
34, Galib Yasar Rahman.
Yes, sir.
Roll number 36, Nusrat Jahan Ramesha.
Yes, sir.
Good. Roll number 38, Mustafa Al Faisal. Mustafa Al Faisal, roll 38. Roll number 40, Mahatab bin Rashid.
Yes, sir.
Roll number 41, Nuzhat Akila Tushi.
Yes, sir.
Roll number 42, Muhammad Fahim Faisal.
Yes, sir.
Roll number 43, Qazi Rubayat Hussain.
Yes, sir.
Roll number 47, Abdullah Al Adib. Abdullah Al Adib. Roll number 49, Nahin Ibn Akbar.
Present, sir.
Roll number 50, Muhammad Zahid Hasan Shubho.
Yes, sir.
Roll number 53, Nafiul Islam.
Yes, sir.
Roll number 54, Syed Tanzib Mahmood.
Yes, sir.
Roll number 58, Muhammad Takvir Rahman.
Present, sir.
Roll number 59, Muhammad Mustafizur Rahman Joy.
Yes, sir.
And roll number 60, Naimul Haq, Naimul Siddiq.
Yes, sir.
Thank you very much.
Present, sir.
Roll 19.
Yes, sir.
তুমি কোন সেকশনে? তুমি roll 19. 19.
Section B, sir.
Sir, assalamu alaikum, sir. Sir, roll 22 present, sir. Section A.
Hang on, roll 22 হচ্ছে নিয়াজ মোহাম্মদ জাহিন।
Yes, sir. Section A.
ওকে, আর রোল নাম্বার 19 কোন সেকশনে তাহলে?
Section B, sir.
Roll number 19.
Yes, sir.
Abul Kalam Azad. Okay. All right. So that's it.
38.
Oh, তোমরা এত পরে আসো কেন? আমি কি রোল নাম্বার করে সময় কাটিয়ে দেব নাকি? Roll number 38, Mustafa Faisal. I mean, next week থেকে I wouldn't tolerate anything later than 5 minutes. Please bear in mind. কারণ আমরা যখন পড়াতে হ্যাঁ নিয়েছি কিন্তু তোমরা এত দেরি করবে না। ওকে, সো প্রথম ক্লাসে একটু আমরা অ্যালাউন্স দিতে পারি। So what I'll do, I'll just share my screen with you and then we'll have a discussion on various issues. And the first topic to discuss is about myself. Obviously, I'm not known to you and I'm actually fairly new to this institution. So let me first introduce myself. My name is R.G.M. Hasan. I've got lots of big names, so I decided to keep it small. And I'm currently living in room number 1009. And if you can note my email address, please, all of you, it's riaz.hasan, REAZ.Hasan with one S at me.mist.ac.bd. And especially the class representative, make sure you send me an email and introduce yourself so that I can communicate with you from now on. So the topic that I'll be covering would be within this heat transfer equipment design. It's a large topic, and that is a heat transfer from extended surfaces. Obviously, I don't want to stick myself to just giving you just the equations and etc. I shall talk about various other issues related to heat transfer. There is a reason for it. I feel that I have been involved in this heat transfer and related subject for a very long time, and this is an interesting platform to share my experiences with you. So academics always they take some liberty, and I enjoy that liberty to speak to you, getting ideas from you, and also translating some of my ideas to yourself. Okay, so I shall start the recording a little bit later after the next slide. So in the next slide, I think it is not, it is quite relevant because we didn't have a chance to see each other. And in this semester, unfortunately, there is no chance because I'm not taking any laboratory with you. My office is probably, Professor Deepak Kanti Das. Do you know him?
Yes, sir.
Yes,
Okay, so I'm just sharing the office next to him where Professor Kamrul Islam used to stay. So he has now left to Buet. He's an emeritus professor, and both of them were my teachers when I was studying at Buet. So let me start my little, some background. So obviously I studied at Buet, and also I studied at London Imperial College. I was a faculty at Buet for a fairly long time. And then I was a faculty at UK for several years before coming here. Obviously, it's not one university I work, but because it's quite common for academics these days that they change. They change for various reasons. And I had my reasons to move around, which I did. And in the end, it's a learning exercise for me. As far as my work, I'm mostly an academic person, but I have also worked in industry for some time, and I have done numerous industrial projects in my career, which spans, as you can see, fairly long time. And also I have been doing research over all my academic career because I love it. I also worked as a consultant for various industries and various companies. These are some paid work, sometimes overseas consultation work involving, fairly high-level companies. So during which career, my subject specialism, as you can see, is basically fluid dynamics and heat transfer. When I first did my studies, first studies means when academics talk about his studies, they refer to their PhD study, okay? So our academic career basically starts after, during the PhD time. And then I did computational fluid dynamics. That's when I started. And then I spent for about 10, 12, 15 years working on high-speed aerodynamics. And at that time, I worked in Imperial College. I came back to Bangladesh and then went back to, I worked in a fairly well-known university, Loughborough University, aeronautical engineering department. And at that time, I came into contact with some of the big name aero industries like BAE Systems, which used to be the British Aerospace, Rolls-Royce, etc., etc. So I had the opportunity to see some very interesting high-tech aero applications that were happening at that time. I'm also an experimentalist. So I did CFD, that is my, if you call it, what is my subject. I'm a numerical scientist, but at the same time, I spend a lot of time doing experiments later on. I've also done something what is called life cycle assessment. You may have heard about it or may not. It's like a new tool, something which came up since 2006 onwards, where you try to find out you follow the life cycle of a particular component over its lifetime. And it is particularly valuable in the new era of where we are always talking about things like carbon footprint, like, you produce a certain product and you need to justify whether it is sufficiently environmentally friendly. And how you do that, you want to find out the environmental impact of that particular product. Okay, simple as that. And my main interest in the life cycle assessment was in the context of renewable energy systems. So obviously I'm a very, enthusiast about renewable energy, which I'm actually delivering not a course, but some contents in the final year, ME-403 in the power plant engineering. And if I happen to be here and if you are all in the final year, then clearly about some of the renewable energy systems during that time. So given those things, for the last 20 years or so, I have actually spent most of my time doing research and consultancy and teaching and supervision, mostly in heat transfer. So I've done quite a lot, actually. and my experience in heat transfer, spans from ventilation, spans from natural convection heat transfer in various situations, annealing in industrial applications, including nuclear cooling pond in one of the very big name industries of the United Kingdom. And very recently, I have started some work involving nanofluids heat transfer. This is a new thing which is going to dominate your life, obviously. And also in the heat transfer management, I have been working in battery thermal management system. The reason being, you may have heard that more and more automobiles will be converted to battery-driven vehicles in the near future. The whole world has to act, and we can't be left alone. So clearly, this is an area, battery thermal management system is something which is a very modern stuff, and I'm very proud to be part of the whole research activity that is happening all around the world. So again, within this battery thermal management system, as you can see, the fins design, nanofluids, all of these play a very important role. So this is a very small snapshot of my work. If you are interested, you can Google Riaz Hasan or GM Hasan, whichever way. You can have a look at some of my papers and see what I have done in my lifetime. I'm also a very professional person. I don't, as I said, that I worked in industry. So clearly, I'm a member of the various organizations, including the IEB, which we have. I'm a fellow there. And I'm also a chartered engineer of the United Kingdom and a member of the IMechE, which is the Institution of Mechanical Engineers of the UK. I'm also a member of the ASME, the American one. And also there is another teaching qualification I did. As a result, I became a fellow of the Higher Education Academy. So these are the main things which basically summarizes who I am. So towards the end, the only thing I can tell you that I'll try my best to give you some appreciation of things around heat transfer, and feel free to ask me questions either during the time or after the time. It looks like I'm running out of time in 10 minutes. So in 10 minutes, when it stops, you stay on the line, I will join back. Okay? Anything you'd like to know at this stage? Anything you'd like to know at this stage, or any queries? Okay, you'll have plenty of time to talk to me later on. Okay, so I can start the recording from now on, because this is where we are actually talking about the stuff rather than some other introductory materials. So I'll start the recording.
Recording in progress.
Okay, my topic is heat transfer from extended surfaces. And this is, perhaps you already know, this is a combined conduction and convection. I have prepared my lectures based on the mainly these two books, perhaps more on the heat transfer by J.P. Holman. Which book do you follow?
Heat transfer Sengel.
Sengel. Yeah, Sengel is a good textbook, but at the same time, Holman is also a very good textbook. You can probably get an electronic copy freely by Googling, and I think the 6th or 7th version is probably available online. And I would strongly suggest, if you can, just download it and then use it. There is another textbook recommended by the universities, which is Impropera and DeWitt. So either of these textbooks are all, very good textbooks. But again, nothing is restricted to one textbook at the university level. You need to know the subject, and in order to, improve your understanding, you are free to use, and you are encouraged to look at other textbooks. Okay, applications. Cooling of electronic equipments, there are numerous applications. I think I take you to the last item, that there are numerous engineering applications, including the natural world, where you can see heat transfer by extended surfaces. Electronic equipments, automobiles. I've got a little stuff. I don't know if you can see it. Can you see this? Can you see an item that I'm holding?
Yes, sir.
Okay. And do you know what it is? Anybody has an idea what it is? No idea? Has anybody good in riding bikes, motorbikes? I'm sure.
Sir, it's not visible.
It's not visible. What
Your
about
camera is
now?
off, maybe, sir.
Oh, my camera is off. Okay, just give me a second. Okay, start video. All right, okay. Let me just see. Yeah, the power is on now. Can you see it now? Yeah. Can you see? Yeah?
Yes, sir.
Yes,
Sir,
okay.
it's a cylinder, sir.
Cylinder. So that's a cylinder and intake manifold. All right. And you can see, all these fins. Can you see these
Fins, yes, sir.
extended surfaces there? Okay.
Yes, sir.
So
Yes,
that's
sir.
the cylinder. That's the cylinder. Can somebody tell me which automobile it is? Which engine is it?
Sir, I think, sir,
Motorcycle, sir.
Motorbike. Good. And can somebody tell what's the size of the motorbike from the cylinder? And those who ride motorbikes.
155 cc, sir.
Oh, excellent. I expected my students to know more than me. Okay, thank you very much. It is actually that size. All right. And it's quite interesting. I actually measured the bore and the depth, and then found out that it is actually close to 160 cc. Okay. And it's a very common thing which we see around. And I actually went to the garage the other day with my driver and then found out a dirty one. They asked for 300 taka and then I cleaned it for you. Okay, because I thought, when we talk, yes, let's take a real device and see what it is. And you can see this is the inlet manifold. So what is important in our analysis is this is the cylinder. And we know that inside the cylinder, you've got the piston moving up and down. And during that time, there is a hell of a lot of heat produced. And the temperature, this is a two-stroke cycle, and the maximum temperature, it reaches to about 1200, if I recall correctly. I haven't touched two-stroke cycle for a very long time, but I guess about 1200 degrees C. And then we know that 1200 degrees C does not stay there for very long because at the next stroke, it cools down and so on and so forth. But the problem is that 1200 degrees C heat temperature cannot stay there like that. And as a requirement, the second law is sitting there and it dictates that in order for a system to work, we must lose a certain amount of heat. And do you know how much heat is lost through these extended surfaces? Anybody? Just to the environment? What proportion of the heat that is generated by burning the fuel? Any guess how much heat we lose?
70, sir.
How much?
70, sir.
20%.
So 70%, sir.
70% is probably, 70% in different ways, not really 70% by heat, perhaps about 30%. 30% converted to work and 30% some other ways, I think, through the exhaust as well. Okay, but just through the fins, perhaps you are right, we lose, a huge amount of heat. And that's one of the problems with converting, getting power from the fuels, because the law of thermodynamics tells us that we have to lose a big chunk of energy in order to get some useful work. But that's not the main issue here. We have to lose it, and we have to lose it very efficiently so that we do not cause any performance issue problem, and also we keep the temperature at the right level. So for example, in the case of an electronic equipment, all the electronic equipments, even the laptop you're using or the mobile device, we all know that if it is used or too many apps are running in the background, it becomes hot. The problem is, if it becomes too hot, then all these chips and whatever their performance level will deteriorate. So there should be sufficient, technological infrastructure, if you call it, in order to make sure that all the heat, unwanted heat, is dissipated at the proper time. So this is true for electronic components. This is true for electric vehicles. As I said, electric vehicle is a thing of the future, and there is a huge amount of research going on battery research, especially all the big name car companies. Nissan, I had a chance to visit their battery research center. You're talking about probably half an acre of research laboratory, and I'm sure the same thing with General Motors in the United States or wherever you go. Because if you cannot dissipate the heat properly, what will happen? The battery thermochemical reaction will not happen properly. And there has been one or two incidences where the battery temperature was so high that it caught fire. And then if it catches fire, the big name companies, that if there is one little bad incident, that creates a kind of shock waves around the world, and their business will go down immediately. So this is a hugely important topic. It's not only that we will study, look at the equations and everything, but its application and its importance in the industrial sector is just sorry about the problem, something beyond my control. So I'll start the video again. Okay, so where we finished is basically, just share the screen again. Okay, so this is where we finished. We talked about the different kinds of cooling issues, and I will start the recording again.
Recording in progress.
Okay, can you all hear me? Hello, can you hear me?
Yes, sir.
Yes, sir. Yes.
Yeah, that's fine. So I finished at the stage of when I was talking about battery cooling in electric vehicles. This is such an important thing. And for you guys, you are going to be the future engineers of the world. You will definitely be involved, whoever going into some kind of research or business or whatever car related, you will hear a lot. And this is one of the biggest problems, that to make sure that the battery temperature remains within a small range of 28 to 40 in order to perform its best. If the temperature goes beyond too much, the battery performance will deteriorate. And there has been one or two instances where it even, they call it a runaway condition, means it became inoperative. And it's almost like, think about you are on a car, a big car, which is driven at high speed, and suddenly the engine is not providing any power. It can be really serious matter. So this is something where a lot has been happening, and within the battery thermal management system, obviously looking at how you can dissipate the extra heat is an important thing. So yeah, it is important. You know about all other things, compressors, transformers. If you look at any transformer next time when you go around, you can see some extra material added to it. They are basically the fins, because the transformers generate a lot of heat, and that has to be dissipated to the atmosphere. And we can see the radiators and the refrigerators at the back of the refrigerator. Those who have refrigerators, you can see some black coils, and those black coils, I don't ask you to touch, but obviously if you go near, I'm sure you know that they're heated. The reason they're heated is they're actually losing the heat, which is being absorbed by the they call it the refrigerant from inside the evaporator, and it is lost to the environment. And you always think about how you can make it very efficient in terms of losing the heat. And whenever that situation comes, you need to talk about a proper design. And that's where we come in this course. So some of the textbook pictures I want to show you. You can find these in any textbook. I think I've taken it from either in DeWitt or I think it's from DeWitt. So you can see here that there is the liquid fuel going through it, and these are the coils or with extended surfaces. So by having extended surface, it allows the heat to be dissipated, and there is it can be gas flow, it can be air flow, whatever. And this is the again scenario, liquid flow. Have you done heat exchanger already with Group Captain Zahid?
Yes,
what
sir.
did you do?
Sir, heat exchanger kora hoyse sir.
আর কি টপিক শেষ করেছো তোমরা লাস্ট
only heat exchanger.
Heat exchanger.
Only heat exchanger we studied, sir.
ওকে, এবং তোমরা আরেকটা হিট ট্রান্সফার কোর্স করেছো অলরেডি, তাই তো?
Yes, sir.
Okay, very good. Because if I know where you are up to, it might be easier for me and make it more useful. There will still be some repetition because I like it to talk in my way. And these are again the heat sinks. Heat sinks basically means it takes away all the heats quickly, that all the heat is lost. And this is the sort of thing, if you go to your laboratory, I think there are 1 or 2 stuff there lying around. I wanted to bring it to my session, but I thought when you go to the heat transfer lab, you can find these yourself. Various designs, that's the thing. There is no, one single design for obvious reasons, which we will discuss. And again, pin fins, and these are the car radiator. I'm sure many of you has looked into car, and in the front of the car, you can see this kind of little, all these pipes along with lots of plates there. Has everybody seen such thing?
Yes, sir.
Okay, so these are the car radiators, and these car radiators are the ideal example of extended surfaces or the fins. Okay, so you can see here, you can see there, and it's everywhere. From now on, once you know fins, you look around, you can find there is a fin. And there are some interesting things. I think we like going into Costa Coffee or any kind of coffee shops these days. And quite often they serve coffee in that kind of mugs. I didn't know that, they have got this kind of fin shape. I thought it's more like holding it nicely. And then later I found, no, it is one of the reasons that they are actually fins. And at the same time, it makes it easy to hold. And also it gives a beautiful, nice aesthetic feeling. All right. So your course is about heat transfer equipment design. And when you talk about any design, one of the things is think about aesthetics, that you can do the same thing, but you can do it in such a way that it's not only doing the job, but it is also looking good. Because if it looks good, it is a nice thing. And if you become an entrepreneur, some of you mechanical engineers become entrepreneur, many of them. And then if you're designing a product which is doing exactly the same as everybody else, but if your design is a little bit innovative, is a little bit nicer, it's a little bit attractive, modern, it will sell more, isn't it? And that's the way things work. You need to think in an innovative way. And this might be slightly off the track, but engineering is not about just doing maths and science and calculations. Engineering is more about thinking beyond the boundary. That you try to do things in a different way, in an innovative way. And within that, design perhaps is the best place where you can show your innovation. Okay, so yeah, this is a nice thing, which I even didn't know that it's for that when I started. And these are the various kinds of designs, which some of you, we will only discuss just one category and then show you the equations for the others. Okay, so this is what they call it a, let me just put my glasses a second. Yeah, I'm long-sighted, so I need my glasses to see close by. So these are the radial fins, different shapes. It can be rectangular, triangular, hyperbolic, and these are the pin fins. You can see cylindrical, conical, concave, convex. Designs are numerous, okay? Just make it bigger. Okay. So within the fins, there are two modes of heat transfer that are important. One is conduction, because the first thing that will happen, the heat, say, look at this particular item I have, heat is generated inside this cylinder. And from the cylinder, the heat will first move through the material itself. Okay, so this is the fin material. And then where it starts from the root of the fin, just the root there. That's where the heat will start to conduct, because it is created inside. And then it will conduct through this material. So a large part is basically conduction through the material. And at the same time, what is happening, you have got the quiescent atmospheric air, or you are blowing like that. You are blowing a fan, which will actually take the heat away. In the case of this engine, because this motorbike is actually moving most of the time, so there will be some flow of air. And it's not only during that time. You can always see that in the case of a radiator, as soon as the engine starts, we know that the fans will start to operate. Two things will start to operate. One is the radiator pump, the water pump, because there is an enormous amount of heat which is created, and we cannot allow that to stay there. Because if it stays there for anything longer than a few seconds, the whole system will seize. This will change. It will, before melting, obviously it will change its shape. The lube oil will burn. Okay, so all these catastrophic things will happen. And then the other thing that starts immediately is the fans around, the additional fans. And in some cases, they're all coupled to the same crankshaft, in order to make sure that as soon as the crankshaft starts to rotate, these two things will start to operate. I don't know if any of you have, drive cars. Is there anyone? I'm sure there are. We have lots of people in uniform, and you drive car. Is there anyone who has driven car?
Yes, sir.
Well, I'm sure. Yeah, I'm assuming you have. And then those who drive car, one of the things they know is you have to stop the car if the engine is overheated. You cannot allow it. You just immediately stop it by the roadside, and don't open the bonnet. Keep it there for some time to cool down, because it can be so hot that if you open the bonnet immediately with some extra oxygen, it will catch fire. So the rule is, I'm telling you the safety instruction, stop the car, move away from the car, let it cool down, and then open and see. Okay, you can drive. If your air conditioning does not work, you can drive. If one of the windows not working, you can drive, but if it is overheated, you have to stop. So the first heat transfer is obviously through the solid material. And then at the same time, dissipation to the environment. And that's how the things would cool down. So we are talking about both of these heat transfer taking place at the same time. And I'm sure in your previous studies, you have done a lot, but I will still take the opportunity to take you through to the very basic, which I'm sure you are all familiar with, but I take the privilege of taking it in my way. So that's the Fourier's law of heat conduction, which I'm sure all of you remember. Am I correct?
Yes, sir.
Very good. And it is a one-dimensional steady-state equation, which you write Q equals to minus Ka delta T delta X. And Q is the rate of heat flow in the X direction. It's measured in watts. Area is the cross-sectional area normal to the heat flow, which is measured in square meter. And delta T over delta X is the temperature gradient and is Kelvin over meter. Some books use it degrees centigrade over meter. Okay, I tend to use Kelvin, but both of them are equally correct. And instead of delta T delta X, you might like to write dt dx, whichever it is. It's just a finite form. And K is the thermal conductivity. And the unit of thermal conductivity, if you put all the units there, is its unit would be watt per meter per Kelvin. Okay, so that's the basic equation. Now, the implication of the Fourier's law, again, it basically says that more is the surface area normal to the direction of the flow, more is the heat transfer. Okay, so if I take you back to this one, so that basically says that this is a fin. If you make the fin very thick, the thicker it is, the more heat will transfer through conduction. But we will see later that making it thick is fine. You are transferring more heat by conduction, but that's not enough. You also need to dissipate it by convection to the outside environment. And also it says that higher temperature gradient causes higher rate of heat flow. It's a general observation that we have. And the negative sign, does anybody know the reason for the negative sign?
So dissipating.
No.
High to low.
Why do we have a negative sign there?
Heat
Minus
transfer from high
Ka.
to low temperature. That's why we negative.
Sorry?
Sir,
Why
high
is it-
temperature to low temperature. That's why we use negative.
Yeah, but high temperature to low temperature, that's fine. So why do you need a negative sign there?
So because we are losing heat, sir.
Yeah, but why is a negative sign? It's nothing to do with that. It's just a mathematical way of, okay, let me just take you through. I've got-
downward stage on sir.
It is two things. One is temperature is going down in the positive direction of X. Let me just show you that. I've got a little bit of technology, the whiteboard. So this is the first time ever I'm using it. So bear with me if I fail, but I hope I shall be able to use it. Okay, to explain that. All right, this is my experiment to myself. Just bear with me. So I will stop sharing this one and I will open a whiteboard. Okay, so let me see what I can do. I'm sure I'll be able to do it. So I close that and then open the whiteboard. Okay, I go to new share and then, yes, I'm nearly there. Can you still hear me?
Yes, sir.
Okay, so I'm talking to myself, but it is important that you are connected. So you can now see the whiteboard, yeah?
Yes,
sir.
Very good. So I shall now explain to you the reason for this minus thing. It's quite interesting. You may have already known it, but why not? Okay, so let me just do it. So let me just write down K. What did I do? Okay, so I shall go to the eraser. Okay, and then if I do this is fine. And then I think I go to draw. Yeah. And then I go to the first one. Yeah, Captain Anis just taught me at 8:30 in the morning. So let's see. If I fail, it's his fault. If I am successful, he needs the, oh, well, let's see. Let's see. So I go to the eraser. And then, where am I making a mistake? No. So, okay. Eraser. Start again. I have to. Okay. And then, okay. No, I'm still in the eraser mode. Let's see if this one works. What is the eraser mode? To cancel that. Go to the draw mode. Okay, I think I'm now there. So I write down, oh, it's too thick. Okay. Okay, yeah, I think it should be fine. So let's say Q, okay, and then equals to minus K, consider it as K, okay? Okay, minus KA. Okay, let's see how it is. So it's a line. So DT okay, so that's D, then dx. Okay, so that's my Fourier equation. This should do. And then the next thing I do, I want to draw, say, a coordinate system. So this is my y-axis, and this is my x-axis. Okay, and then I want to show the temperature variation. So the temperature is going from there all the way to there. So let's say this is position 1 and this is position 2. Okay, now if you do delta T delta X, okay, I'm writing, say delta T delta X basically is final minus initial, all right? So that is basically T 2 minus T1. And then you follow the same at the bottom, which is X2 minus X1. Okay, are you with me?
Yes, sir.
Because this basically tells what is dt dx. And the nature of conduction is such that every time x2 minus x1 is a positive number, because you are measuring the the distance along that direction. Okay, this is your direction of measure of x. So x2 minus x1 coordinate is a positive thing. But dt dx is such that T2 is less than T1. So there is always a mismatch between the the change of temperature and change of distance. So in order to take that into account, this minus sign is actually put in. That's the reason we put this number minus. That's the whole reason, that it comes directly. Yeah.
So can you repeat it again, sir? Couldn't get
Yeah.
it.
Okay. I mean, basically, the reason that this minus sign is there because the positive direction of x and positive direction of t are creating a negative thing, because positive direction of x means dx means final x minus initial x. So that's x2 minus x1. Okay. And so this is a positive quantity in the coordinate geometry. And what is happening then to dt? You must put T2 minus T1. And what is T2 minus T1? Whatever be the temperature, it's a negative temperature. So your D2 minus dt over dx is a negative quantity. So in order to take that into account, it is customary to put a minus there. Is that clear to you now?
Yes, sir.
Yes, sir.
Okay, so this is just a little bit of thing. You may have used it all along, but I think that is the fundamental reason of why we have used it. Okay, so let me just clear it. Okay. Oh, I'm very happy about this. I can use it, so I shall use it a lot. Okay, clear all drawings. It's just a matter of getting used to. Okay then, so I can now stop share this one and then move to my new my presentation. Okay, can you see my presentation now?
So yes, sir.
Yes, sir.
Okay. So we have seen this tiny little thing, but these are really intriguing. You ask yourself, these little things, and you can see much more interesting things, especially with the application of maths to real life, because heat transfer allows you to do that. Okay, and then you change the Fourier's law whichever way, and this is how I teach my students all the time, that you convert it in such a way that it is like Q equals to minus delta T over R. You just rearrange that, and that R becomes the resistance, thermal resistance. And I'm sure you have done the electrical equivalent of thermal systems in your previous studies. Yeah. So what is happening is you can convert the Fourier's equation and convert it in the form of I equals to voltage over resistance, because once you can convert your thermal equation into the electrical system, you can actually do a lot more complex stuff, especially you have seen in radiation. Just as a matter of completeness, because when we are talking about the fin design, the material selection is a very important thing. So this is just a reminder of some of the common materials which are used, and you can see the range is huge. When you use copper, you're talking about 386, and going back to cork board, it's an insulating material which goes to 0.043. So have you done thermal conductivity experiment in your laboratory?
Yes, sir.
Good. What was the material you have used? Was it stainless steel or copper, or what was
Copper,
it?
sir.
Copper. And did you get numbers close to it?
Yes, sir.
Yeah. And what other material was there?
We have copper, sir. Copper.
Okay.
Experimental
Okay.
copper.
Yeah. So copper is a highly conductive material. On the other hand, if you come to mild steel, which is a very common thing, say its thermal conductivity is very low, and I haven't put stainless steel, but I would encourage you to look at the thermal conductivity of stainless steel in your spare time, because stainless steel thermal conductivity is very low. If I recall on top of my head, it's perhaps between 10 to 12 or something like this. So stainless steel itself is a highly insulating material. It is the steel ferrous material, but having all those different alloys there, alloy material in there, its properties change very, very drastically. So we need to know, some of the things, because in design, you are free to choose what is available. You are also aware that the thermal conductivity changes slightly for different material. For example, with water, you can see there is some change, etc., etc. So this is just a recap of the work. And the reason I'm saying all these things, because towards the end, I shall talk about the fouling in fins. And during that time, we will probably use this electrical analogy approach. And again, this is something known to you, that the flow of heat and the flow of electricity are very, very analogous. Although they are completely different things, but they have got a lot of similarity. Let's say, for example, if you look at the fundamental equation, this is the Fourier's law and this is the Ohm's law. They're very similar. Temperature difference is the reason for heat flow, and electrical potential is responsible for current flow. May I ask you all to make sure that you understand means from your deeper sense. You have absolutely no issue of saying what is heat, what is temperature. Because I ask these questions to many engineers, even fairly experienced, good engineers, and they cannot tell what's the difference between heat and temperature. They can tell, yes, sir, heat is joules, temperature is degrees centigrade. But that's the kind of a layman's approach. When you become an engineer, you must have the appreciation. Heat is the total energy content, and temperature is the potential. So the temperature drives the heat to flow. So they are completely different things. And as a mechanical engineer, you should not make this, wrong use of the terminology. It really feels very frustrated when people tend to forget, especially if you're an engineer, mechanical engineer, what is heat, what is temperature. So temperature difference responsible for heat flow, and electrical potential responsible for the current flow, and thermal resistance, electrical resistance, and also heat energy transferred without physical movement of particles, electrical energy transmitted without physical movements of particles. So there's a huge amount of similarity as a result. I'm running out of time again, but again, I'll rejoin once it is finished. So we go down again, and can I ask you quickly, very quickly, it wouldn't take more than 2 minutes to find out this. Tell me the result and tell me the unit of the quantity that you are. So it's a brick wall. One side is at 40 degrees C and the other one is 10 degrees C. You find out the heat transfer per square meter of the surface area. The brick is 250 millimeter thick. The K is 0.52 watt per meter Kelvin. So I'll do it on a paper while you are working, and then I shall talk about it. I don't need to do it on a whiteboard because it's too simple. So you basically Q equals to Ka delta T over delta X, and area is, you are asked to find out per square meter. So that's Q over A. So K times delta T over delta X, and K is given as 0.52. Delta T is 40 minus 10, so that's 30, and delta X is 250, so that's 0.25. Can you tell me the number, please? What is the Q by A? $62.4. Okay, that's fairly straightforward and interesting. What is its unit? Watt per meter squared. Is everybody with that? Does everybody agree that its unit is watt per square meter?
Yes, sir.
Good. And what is the name of this quantity? When I say watt per meter square? Yes, very good. It is, yeah, no, it's not power. It's called heat flux. Okay.
Flux,
so
sir.
I'll write down the name of that quantity. I'm not sure if my if this will work. Yeah, I think it will work. So basically Q divided by A, and that's equals to heat per square meter, and the quantity we are getting 62.4 watt per square meter. And this is what is called heat flux. Okay, do not forget it. When you say flux, that automatically means per square meter. You may have, you are more comfortable with electrical different fluxes, but it is exactly the same thing. Okay, I think the time is 10:17. So I want to, come out of it now and then rejoin. That would be the best thing, okay, before they stop. All right, so you stay on the line. I'm going out and then join. I think I need to end the meeting and then you rejoin, okay? It is a case of a, I'll start recording.
Recording in progress.
Okay, I think we are there now, and most of you are there. So if it is a case of a cylindrical polar coordinate system, which is flow through a heated pipe, you have done plenty in your heat exchanger, so there is no point repeating this. And this is steady state, one dimensional with respect to cylindrical. You apply the Fourier law, it's the same law, and then you can find the heat transfer in using that kind of relation. Let's move to convection then, because it is dominated by two things. Heat transfer by physical movement of the fluid particles. In this case, lumps of fluid. Are you with me? Can you hear me? Can you all hear me?
Yes, sir.
Yes,
Okay.
sir.
Yeah. So lump fluid carry heat energy from one place to another, and two types of convection. One is the forced convection, and another is free or natural convection. So if it is a convection, you all know that this is a fundamental equation. Q equals to HA delta T, whatever be the script, just ignore it. It's basically HA delta T. And the main difficult thing here is A, straightforward. You can take a ruler, find out the the geometrical things and calculate what is the A. When it comes to temperature, the only you need is a thermometer, a thermocouple. You find out the two temperatures, job is done. But the messy thing and the difficult thing is knowing the value of the H, that what is its value? And the difficulty with this quantity H, that it depends on so many different factors that the value of the H can only be found in various ways. And even when the value of the H is found, many equations exist. All these level of error in the results can be very high, plus or minus 50%. In some cases can be plus or minus 100%. So this is a very tricky quantity. So I take this opportunity for you that this H actually relates to the boundary layer, because ultimately the heat which is transferred, I shall take this opportunity because I have now a little bit more techno expert. So I shall use the board to show you the heat transfer by convection. I'm sure you've done it, but I want to do it in my way. And then I shall show you one interesting YouTube video to show you what is a boundary layer and what is happening there. Okay, so I shall get rid of that and then open So I stop sharing that and then open up a whiteboard. Okay, start share and then open up the whiteboard for you. Okay, so I should just draw so I'm in the draw mode. Okay, so let me just draw a little surface and then see what happens to it. So where is the pen? So I'm in the draw. So just do that. So if that is the pencil, okay. All right. So let's say this is a plate. And then the plate is kind of insulated at the bottom. And the plate is at a temperature of, I put some numbers there, 100 degrees, okay, C. And then let us assume that there is some flow of air over to it. And let's say this is air blowing over it. And the air is coming at a temperature of, let's say, 20. So what will happen? As soon as the air comes in, so by the time the air leaves, the air, let's say its temperature is 50. I'm just putting some numbers to make it more realistic. So what is happening here? Heat is actually lost from this heated surface. And if you come closer and closer and closer, can you not think that the closer you are, the temperature is higher? And if you come, very, very close to the surface, that's where heat is being dissipated right from this surface to the molecule of air which is there. And that transfer is happening in a region which is called the boundary layer, okay? Which is called the boundary layer. Means a layer of the fluid which is affected by the proximity to the solid surface. And obviously, what is the velocity of this one? the velocity is 0. And if this velocity is, let's say, 10 meters per second, so there will be a region extremely close to the surface where the velocity will be almost negligible. So there will be almost a stagnating layer attached to the surface, and the main heat transfer business starts at that point. And then that heated particle will be swept away because the air is coming at a high speed. So that's the fundamental scenario that happens when the forced convection takes place. That it's all about a boundary layer where these interesting things are happening. And again, it is because of the boundary layer. You will see the uncertainties. I shall show you first a video, which is an experimental video, and then we'll make some approximations to make you understand why the value of the H we get in all different interesting equations can be very, very different from what happens in reality. Okay, so with that little introduction, I'd like to now go back to my slide, and then I shall actually open up. You just stay with me. I shall open up this particular YouTube video, and then let's watch it together. So can you all see my Google one? Probably
sir.
not. No, probably not. Let me just then share. I stop this screen. Okay, I stopped that one. I need to now share. If I go to the share screen, I need to share the whole screen, isn't it? Yeah, I need to share the whole screen, desktop. Okay, hopefully you'll be able to see now. Can you see my Google page?
Yes, sir.
Okay, so I shall now open the YouTube video, which is few minutes, and then let's watch it together. It's especially developing turbulent boundary layer on a flat plate, one of the big name universities in Australia. So let's have a look. Oh, I need to start it. So it's a water tunnel, and within the water tunnel, I need to close this. Within the water tunnel, they're actually pulling a plate and taking some pictures. This is plate, all right, which is being pulled in water, and then these are the pictures they're taking with specialist cameras, that what is happening to the fluid which is close to the surface of, you can see lots of bulging motions, and that is all about boundary layer. You can see the Reynolds number somewhere. Plate velocity 0.22 meters per second. eruption of a whole strange whether the transfer is soon.
Sir, you are not audible, sir.
Your voice is lagging, sir.
Recording stopped. Recording in progress.
Sorry. Okay. Can you hear me now?
Yes, sir.
Okay. All right. So I think you had some appreciation of the YouTube which showed the boundary layer on a flat plate. Yeah. Have you seen it? It's very strange kind of region, very close to the surface. And the problem is, in the case of heat transfer analysis by convection, it all starts from there. You just cannot avoid it. And this is the reason that no matter whatever you do, the value of the H which is calculated is a heat transfer coefficient. It depends on the facts that's happening within the boundary layer. And that makes things really complicated. Okay, I'm sure you have discussed a lot about all these things in your analysis, but again, I wanted to do it in my way. So this is, I'm sure you're familiar with this sketch, that this is a simplification of the flow over a flat plate, which is heated. So this is a heated plate, and the air which is blowing over is actually taking away the heat from the surface. And there are two temperature. The temperature gradient is like that. It is highest at here and leads to ambient condition after a little while. On the other hand, the velocity profile is a completely different thing. Okay, and the boundary layer thickness is delta. Some regions are called turbulent. Region can be a very smooth flow, which is termed as turbulent, which is termed as planar. This is what we saw in our picture. It was the upside down, so I decided to draw it in that way, but it is the same thing. So certainly you will ask me, sir, oh, what have you done? We have seen a completely different thing. We have seen all these curly motions, all this vortex eruption, very irregular motion, whereas we are actually making a simplification. Well, this is where we are stuck. When we do the analysis, we have to make some simplifications. And this is why boundary layer thickness, where the free stream, the velocity there is 95% of the free stream velocity. That's a standard practice. That if the velocity is 10 meters per second, we say that this velocity is about 5 to 10% less. So let's say if it is 9 meters per second, we say this is the end of the boundary layer, because otherwise it becomes very, very long, very high. So that's how we work. So what we see in the boundary, that the thickness is variable and difficult to measure accurately. Velocity varies in the boundary layer, and the heat transfer, this is the unfortunate bit, heat transfer depends on whether the boundary layer is laminar, turbulent, or transition. So your heat transfer coefficient, which we are after, depends on so many uncertain physical situations. And there is no way you can avoid the boundary layer when the heat transfer is involved. Even when you are talking about, very, very high speed vehicles, you're talking about hypersonic vehicles moving at Mach number of 5. There is a very thin boundary layer right on top of the wings or whatever. There is this boundary layer, and the heat transfer starts from the solid surface, and it has to. There is no way that it can go straight to the material. It has to go through the, through the boundary, and that creates a huge problem. And again, I'm sure you have all done some sort of dimensional analysis in your previous studies, Buckingham Pi Theorem.
Sir, we
Yes,
have done it
somebody
in
can-
fluid mechanics, sir.
You have done it fluid mechanics. Yes, fluid mechanics and heat transfer are taught together. You have done Buckingham Pi Theorem, okay? Good.
Yes, sir.
It is important that you have some appreciation. You don't need too much, but just an appreciation of what it is. So in this case, what is happening? We can say that the heat transfer coefficient H is a function. We're not saying what it is. We're saying that it depends on what? It depends on the properties of the fluid. So if your fluid is air, it will have one kind of heat transfer. If your fluid is water, it will have a different kind of heat transfer. If it is an oil, it will have another kind of things. So mathematically, what is required are the fluid properties. And what are those? This is viscosity. Are you comfortable with the symbols?
Yes, sir.
Viscosity, density, thermal conductivity, and the specific heat at constant pressure. Okay, so these are the 4 quantities that defines our fluid. And then it depends on the V, that what is the approximate velocity, typical velocity with which the fluid is approaching. We call it a characteristic velocity. And then obviously delta T will be there because this is an important quantity in the analysis. And L stands for some kind of geometrical representation, and we call it a characteristic linear dimension. To put it more, in real life terms, if it is a pipe flow, we could say L is basically the diameter D. If it is a plate, we can say the width of the plate, for example. Okay, so some sort of characteristic length is there. And the way we do the dimensional analysis, which you are all very familiar, you have probably used the MLT system. Am I right? Mass, length, time?
Yes, sir.
Okay. We can even extend it for any number of primary variables. So in this case, the analysis has been 2 more primary variables has been put in. Have you done this one as well? 5 primary variables?
Yes, sir.
Probably, yeah. So in that case, we are using 5 primary variables: mass, length, time, and also you have used heat and also temperature T, okay, just for convenience. And then we have expressed every single quantity in the form of the MLT system. So for example, take the simple one. For density, we have used ml to the power -3, characteristic dimension L, free stream velocity L over T, and etc., etc. So you express them in the standard fashion and follow the dimensional analysis approach, either the Buckingham Pi Theorem analysis, or another way is this. You basically express this in the form of quotients. That is also possible, like, H is a function of mu, rho, K, Cp, delta T, V, L, etc., etc. And we use unknown coefficients A1, A2, A3, etc., etc. And then you can extend it to a number of series variables, but there is no need for it. We can just use the first one. The whole point is we are saying that H is expressed by this, where we do not know the values of A1, A2, A3, etc., etc. And then by doing the standard manipulations, where you express all these things into MLT HT, and then combine get algebraic expression by equating the coefficients of M's, L's, T's, etc., etc., you come up with this relation. Okay, that you can convert them into them, And finally, you actually express them in the form of this. Okay, do you think I need to give you any more derivation at this stage? Because this is not our main concern. I'm assuming you have understanding of it from previous knowledge. Am I right?
Yes, sir.
Okay. If you need, obviously, I'm happy to discuss these things, but these are kind of should be known to you from your previous studies, but it's not really very important. What is important is we have expressed all these things in the form of an equation like this, combined them. And when you combine them, you have come up with non-dimensional numbers. And I'm sure you're familiar with Reynolds number already. You are familiar with the Prandtl number. I'm not sure if you're familiar with Nusselt. You are, because you have done heat exchanger and heat transfer, so Nusselt number. And this Nusselt number is H, I'm using L, but if it is a pipe, it is diameter D, okay? And Prandtl number is a property because it's combinations of everything. And Reynolds number basically is the rho Vd divided by mu. Does anybody know the physical meaning that Reynolds number is a ratio of two quantities? Can anybody tell me what it is? What are the two ratio of two things?
Convection heat transfer by conduction heat transfer.
No, not the heat transfer. I'm talking about Reynolds number. It's a ratio of two.
Viscous force by.
Okay, which force is at the top? Inertia force. Okay, inertia force over viscous force. So whenever there is density and velocity, it means inertia. That huge mass moving at a certain speed. Think about a truck moving at a high speed. It has got a huge inertia. It is exactly the same thing, that the fluid moving at a certain speed, it has got an inertia. And mu is the viscous force which acts near the wall, which tries to oppose the flow. So again, all these quantities have got different meanings. But what is important to realize here, that in this relation, we have got Nusselt number as a function of Prandtl number and Reynolds number, but with three unknowns. One is a B, another is an M, and another is an N. And the way to know these things is basically you do loads and loads of experiments and then relate the experimental data in this fashion and then find out the values of M and N. And by doing so, you come up with loads of interesting relations. But obviously, you must have realized by now that although we have got a beautiful relation, beautiful equation, but end of the day, it is based on a huge simplification of the actual process of convection heat transfer. As a result, the values of H you will get are likely to be quite different from what it will be in experimental situation. So can I ask you quick this session, because our class should finish at 10:55, isn't it?
Yes, sir.
Okay, so can I ask you all to quickly have a go at this problem and find out the value of H? Can you all read this question and then draw a little sketch, and then if you want, you can make a note of the problem quickly on your paper. You don't have to write, calculate 8 millimeter diameter, mass flow rate 1.5 kg per second. This one quickly, and then we shall solve it.
Recording stopped. Recording in progress.
Okay, have you written down? Hello?
Sir, you got disconnected, sir. We couldn't wrote it down, sir.
Okay, can you see now? Can you see my screen?
Yes, sir.
Can you now see my screen? Hello? তোমরা
Yes, sir,
দেখতে
we can
পাচ্ছ
see.
আমার screen?
জি স্যার দেখা যাচ্ছে।
Okay. Can you quickly just make a note of this and solve?
Sir.
Tomorrow morning.
Sir.
আপনার কথা
Sir, you are not audible, sir.
আপনার কথাগুলো না স্যার ল্যাগ করে আসছে মেবি ইন্টারনেট প্রবলেম।
Hello.
Sir, if you upload the slides and the class video in the classroom, sir, it will be better for us, sir.
Recording stopped. Recording in progress.
I think you can hear me now.
Yes, sir.
Yeah. Can you just copy this one? And what I can do, the class rep, if you send me an email, then at least I can send this problem for you to try this afternoon. And tomorrow when you come back, at least we know that we are singing together, because from then on, I will move on to the fin business tomorrow at 8 o'clock. So the class rep, can you email me immediately after the class, and then we shall, I'll give you this problem for you to try. Okay?
Yes,
so that's all for today, because I need to stop now. And I need to stop now, and then by email you can then get the get this.
Sir, attendance.
Your class rep. Okay, thank you very much, and then we shall continue. Hello.
Sir, hello.
আমি already নিয়েছি একবার।
স্যার,
হ্যাঁ বলো।
এই যে রেকর্ডিংটা স্যার একটু দিয়ে দিন স্যার।
হ্যাঁ বলো।
স্যার
রেকর্ডিংটার পিপিটি ফাইলটা একটু ক্লাসরুমে দিয়ে দিতেন স্যার।
আমি পিপিটি ক্লাস মাঝে মাঝে দিব, কয়েকদিন পরে পরে, not after every class। আমি একটা সেশন শেষ করে তারপরে দেবো তোমাদের।
Sir,
আমি
class
গুগল
20
ক্লাসরুমকে, হ্যাঁ আমি ক্লাসরুম ঠিক করেছি। ইউ উইল নো অল দিস ক্লাসরুম গুলো আমি সব তোমাদের ক্লাস রিপের মাধ্যমে জানিয়ে দেবো। ওকে, তো আজকের জন্য এখানেই আমি শেষ করছি।